Welcome back to another video. I know I said today, I don't know how many people are really keeping track, but I said today I was going to do like 10 hours. I think I got to do it next week because I didn't get much sleep yesterday. So that's a real tragedy. I'm still probably going to do a good amount today. But anyway, take a look at the GitHub followers. We have reached 100 followers. That is so hype. Thankful to all of y'all. Thank you so much, guys. All these people. These are my goats right here. Gotta make the Pokemon sound of the day. That Pokemon is Zubat. If you ever played the games, this cry will sound pretty familiar. I didn't want to do the one from the anime because it's not as iconic as this one. So let's take a listen, shall we? All right. Let's get into the Leetcode of the day, shall we? See, look how late it is. 9:51. Oh, wait, another easy. Okay. Okay. This is a little tricky. Because I don't really know. Okay, so I record this first letter, I guess. And then I'd record this last letter. And then I'd record this letter. And then I record this letter. And then this letter. So in the end, I would have LEESSDDL. So if I just rearrange this to put the L, so just like I just delete this one and then do it like this, we can see that I mean, it doesn't have to do that. Like I would check like, are these the same? And then I would check these the same, these the same, these the same. Okay. Okay, but now we have to code it up. So, okay. Circle. It's going to be a little bit of an array. And then I guess it's 4 character in circle in sentence. I guess we can start off with maybe the best way to get all the words or like is like I keep adding. Okay, so like words, right? So it's like ifs. So you got like word equals bang, and then it's like word if C doesn't equal a space, word plus equals C, else words dot append word, and word is now blank. And if words dot append word. And the reason we need to do this last check at the end is because there's no space at the end, right? So it's gonna have the word is gonna have delightful in it. So if we just print out words here, we're gonna notice that, well, we should notice that it's gonna have all 4 of these, right? Awesome. So now what we're going to do, guys, is very simple, right? So now what we're going to do is we're going to loop over every word. So for word in words, right? So like what this is going to print is just, it's going to print Leetcode exercises sound delightful, right? But what we're going to want to do is we're going to want to add them. We want to add the pattern that we noted at the start. So like just a quick refresher on what the pattern is. LEESSDDL, right? Because it's the first one and the last one of every single word. And then using this, we can probably pretty easily figure out if it's circular or not. And the way we're going to do that is we're just going to add circle.append word at spot 0 and circle.append word the last character, right? And then I don't know if there might be like a faster way to do this, because I'm doing like for loops, not like for loops, like the number 4. So yeah, so we'll notice we'll have that, and then we can do like a 2-step algorithm, I guess. It's like for, okay, so we'll just start off like this, right? So if circle at spot 0 doesn't equal circle at spot 1. No, -1. That's the last one. Return false. I just want to see, is that, can you do that? Can you do -1 like that? Because L does not equal, yeah, okay. So now what we're going to do is, we know, man, I don't know. I'm not really thinking about the edge cases too hard right now. I'm just trying to get the general framework out. We know that there's going to be an even amount of these, like, right? Because it's like, if you look at these, this is always going to be an even amount because we're matching 2. So we can do like a for loop. So for I in range. So len of circle. We're going to do -1 because we just checked the other one. And we're actually going to step by 2. That way we can just do both checks at the same time. So if word at spot I, so 1 doesn't equal word at spot I plus 1, return false, right? And then it's gonna step. It's gonna just do both of them. I'm pretty sure I can just do this. Let's just see if that works. I haven't really. I've thought this one through, but see, I'm not really getting what we need for that one. We're just gonna print word at spot I and word at spot I plus 1. Let's see what we're working with. E and L. Is this -2? E and L? What? Is it -1? Whoops. I think it might be, instead of I, it's no, it can't be I -1 because E and L. Why is it? What? Why is it printing L, dog? It's this one, and I plus 1 is E. Again, not L. That doesn't make sense. Okay, let's try -1. I'm a little bit confused here, but E and D. What? Huh? Oh, it's word. It's circle. Oh my god. What am I doing, guys? There we go. Let's just turn that in, see if that works the way we think it does. This is a little bit of a convoluted solution. I don't know. Okay, I guess we beat it. Yeah, I mean, basically, it was just the whole thing we did. We just split it. We just needed to get this string right here. We didn't need to extract that, and that seemed to kind of did it for us. Kind of want to see what other people have done. Let's see what the comments say. This was a definitely harder medium though. This is not not too easy, but oh, maybe it was. What about N difficulty, bro? What? Okay, a good problem for easy level. True. See, like this guy did it way better than me. Oh, that's genius. And I'll be right back to go to the bathroom. All right, I'm back. I think I'm going to redo this problem with this secret strategy. Okay. If sentence at spot 0 doesn't equal sentence at spot -1, return false, and then for I in range 0 to the length of sentence, if I'm gonna go C equals sentence at spot I, if C is equal to a space, if sentence at spot I -1 doesn't equal sentence at spot I +1, return false. Is that all you need for this function? Unbelievable. That's a beautiful, cute algorithm, bro. I would not have, man, I probably would not have come up with that, honestly. Okay, so I was gonna do the LRU cache one for me yesterday because I was super confused on it. This one. Okay. Do quit your job and start making games. Jonathan Blow made me quit my job. Jonathan Blow on simplicity. You watch one Jonathan Blow video, and here we go, bro. I don't even got a job. Neatcode. IO. LRU. Cache. This is a hard.
Hey everyone, welcome back.
Neatcode. What was that problem? The DP problem that was like really hard. I need to find it. Where is it? No, not here. I swear you can just go on profile and it just show you like your streak or whatever, and then it's somewhere there. No? What is the locked badge? Oh. This is kind of cool, dude. People at Leetcode really be hustling with this UI and stuff. It's kind of dope. Dude, where is it? What was the problem? Oh, minimum total distance traveled. Minimum total distance traveled. Nope.
Hey everybody, this is Larry. This is me going with Q4 of the weekly contest 318, minimum total distance traveled. Hit the like button, hit the subscribe button, join me on Discord. Let me know what you think about this problem and this contest. So looking back, I did about 13 minutes on this. To be honest, I really was convinced that there's another way to solve this, and that is using a very high machinery called min cut max flow, or min cost. Min cost, min cut, max flows.
What is this guy talking about?
Specifically. But yeah, we'll see if this works.
Okay, guess we're never gonna know how that one works.
Let's write some more Leetcode today. Let's take a look at a really popular interview question. LRU
Is there background music?
cache. It's even asked by Twitch TV. It's one of their most popular interview questions. And also, don't forget to like the video. It supports the
Why is there music in this video?
channel a lot. So this is definitely more of a design problem
it's gone
than
now.
an actual algorithms problem. So we have some kind of
The frick?
cache that's going to store values. It has a capacity, so it's fixed size. And we want to be able to get values from this cache based on a key value. If that key value exists, then we'll return the value that it corresponds to. If it doesn't exist, the default value we want to return is -1. And if we're getting values, we also need to be able to put values into the cache. We're putting them in based on key value pairs. And there's a lot of edge cases, and they explain a bit of them to us. If the key already exists in the cache, then we just want to update the value. If it doesn't already exist, then we're inserting it for the first time so we can put that key value pair into the cache. And remember, this does have a fixed size capacity, so if we ever exceed the capacity, then we have to evict the least recently used. So that's why this is called the LRU cache problem. And it also makes sense, right? If there's a key that we're not really using, then that's the one that we're going to take out of the cache. And this is actually pretty similar to how browsers work. So for example, if you're using Chrome and web browsers have caches, if there are values that we're not really using in that cache, then of course we can remove them. Let's also try to solve this the most efficient way, which is each of these operations, get and put, are going to be constant time operations. And it's going to be kind of tricky, but it's definitely possible. So let's just look at the first example. So the input is 2. So that's something that we need to kind of remember, right? The capacity is 2 in this case. And the next operation is put. So we're putting a pair of 1, 1, key 1, value 1. And we're going to keep these kind of in order, right? Because we want to remove the least recently used. So we got to kind of remember in what order are we adding these values in. The next one is another put operation, and we're putting 2, 2. Of course, for these first 3 operations, we're not really returning anything. So the output is going to be null. So next, we're actually doing a get operation, and we want to get the value that has a key of 1. And remember, we're trying to do this as fast as possible. We're trying to do each operation in constant time. So how can we know instantly what the value is when the key is 1? Well, the easiest way to do that would be with a hash map, right?
True.
So we're going to use a hash map
True.
to instantly look up the value of every key.
True
we
that.
can, of course, do this in constant time, and we know that the size of this hash map doesn't need to exceed our capacity, so we can have only 2 values here, right? So for the key value, we can use the same value that we use for each of our nodes. And for the value, we could also do the same thing. We could use the same value that we use in our nodes, but I'm going to show you why it's going to be a little bit better for us instead to have the value be a pointer to the node itself. And we can do the same thing. Why it's going to be a little bit better for us instead to have the value be a pointer to the node itself. And we can do the same thing with the second node that we inserted as well. So for key value 2, we're going to point at this node. So now finally, when we call this get and we ask for the key 1, we're going to return the value 1 that's over here, which is exactly what the output tells us is correct. So since we just used the get operation to get this one, we went to our key, then we found this value, and then we returned that value. That makes this the most recently used value, and this is the least recently used value now. So I'm going to keep track of the most recent and least recent by having a left and right pointers, right? So this left side is going to be the least recently used, and the right over here is going to be the most recent. So therefore, we're basically going to be swapping these two nodes, right? And so this portion of the problem is starting to keep the ordering of these. It looks like we're going to need a linked list. And not only a linked list, but a double linked list. Because remember, we can easily look up where these values are, but if we want to also reorder them quickly by for example, every time we use a get operation, we want to take this value and then move it over here because it was the most recent. And so now we're going to reorder the two nodes. So now this is the least recently used and this is the most recently used. And since this is a doubly linked list, we need the pointers to be connected. Of course, the hash map won't really need to be updated because these are pointers. They're already going to be pointing to the correct ones, and I'm not going to show that. And now we can get to the most interesting operation, the third put. So we're putting a third value, key value, 3, and since 3 is greater than our capacity of 2, then we're going to have to remove the least recently used value, and convenient for us, we know exactly what that value is. So first, we're going to end up updating these pointers to make the least recently used 1 and get rid of this. And of course, we want to replace that 2 since we know it's the least recently used. We want to replace it with the new key 3. And now we also want to update that pointer. We want it to point at the new node. And since the new node 3 is the most recent, we're going to put it over here, 3. And the pointer is going to point here. This pointer is going to point here, and there's going to be a double link between them. So this is basically the main idea. We're going to keep track of a capacity. We're going to have a double linked list. We're going to have a hash map where the key of the hash map is going to be the same key that we get from the input, and the value is going to be a pointer to the nodes. And each node is going to look something like this. And it's going to have 2 pointers, remember? So it's going to have a previous pointer and a next pointer. And don't forget about this right and this left. These are also going to be nodes because we want to have pointers. We want to be able to instantly know what's the least recently used and what's the most recently used. So these are going to be dummy nodes pretty much. So getting into the
Dude,
code,
I don't get it.
Remember, we're going to need a node.
Like, I really don't get it.
Even write this LRU cache class, let's make another class for that node that we're going to use. And remember, each node is going to have a key value pair. So we're going to get those. We're going to initialize those. And we're also going to have 2 pointers, one for the previous node and one for the next node. And they're both going to initially be set to null. Now when we actually get into the LRU class, we know that the capacity needs to be stored because we want to know if we ever go over that capacity. We also need a hash map, and I'm going to call that our cache. And remember, this is going to map the key to nodes. And before we even have any values in our cache, we want to have a couple dummy pointers, a couple dummy nodes, which tell us what are the most recent and least recent values that we added. So we can just initialize these to 0 for the default values, so 0, 0. And initially we want these nodes to be connected to each other, because if we're putting a new node, we want to put it in the middle between left and right. And we can do that with some pointer stuff. So left.next is going to be right, and right.previous is going to be left. And remember, left is going to help us find the least recently used, and right is going to be most recent. So now let's start with our get function, because it's mostly straightforward. If the key exists, so if the key is in our cache, then we can return that value, right? So we can return self.cache of key. Now this tells us the node, remember, because each key is mapped to a node. So to get the value, we can just do .val. And of course, if it doesn't exist, they wanted us to just return -1. Now the only thing we're forgetting with this get is that every time we get a value, we want to update it to the most recent. So to help us with this part, I'm actually going to write a couple helper functions. So I'm going to write...
This is a medium problem, by the way.
I'm going to write a remove and insert helper function. And these helper functions are going to be applied to our linked list. So we're going to pass in the node that we want to remove from our doubly linked list. And I'm also going to write a function to insert into our linked list. And when we insert, we're going to insert at right.
That makes sense.
And the remove is just going to remove from the list.
True.
So these are basically going to be pointer functions. We're going to be manipulating some pointers from our left, from our right, and doing some stuff. So I'm not even going to worry about that. All I know is that we have a helper function that can remove any node from our list, and a helper function that can insert any node at the rightmost position of our linked list. So since we're getting, what we want to do to our list is take this node, self.cache of key, and remove it from our list. And after we remove it, then we want to reinsert it at the rightmost position. So we can just do self.
Both insert wrong.
And looking at this, get isn't so bad as long as we fill out these.
Self.remove, remove node from list. But why are you removing node from list? And you're inserting it. Oh my gosh. Yes, I get it now. Oh my gosh. Dude, I'm actually so tired. I don't know what's going on. Yeah, I'll be right back. All right. I'm back, guys. I'm super out of it today.
These two helper functions for us.
Now let's just okay, so yeah, we're gonna need a class. How did he do it? How did he define it?
This start doing some remove any
Class node. What does it take? Does it even take anything? Key. See, I'm not really understanding this at all. Well, there's a self dot prev. Okay, I know that much. What was the other thing he put in there? Oh yeah. Okay. So we made the node. Now we need to initialize the node in somewhere. See, like, why? Oh, because those are dummy nodes. Right. Okay, so self dot left. What was the other thing? Dot next. Okay. Self dot left. Self dot equals node 0 0 node. And then you make them connect to each other. Is that right? Nice. Okay. And then he makes two of these helper functions, which I need to try to implement by myself here to really kind of get understanding of this problem. Oh my god, def remove. It needs a self and it needs a node. Does that have to be capital? No. And then a def insert. I don't really get it though. Because I don't really...
node from our list and a helper function that can insert any node at the rightmost position of our linked list. So since we're getting what we want to do to our...
Okay. If key in self dot... Here, I'll call it cache too. In self dot cache, we have to make this, or to do, make most recently used. And then we have to return self dot cache at spot key dot val. And if that doesn't exist, just return -1. I guess. That's where he's at, I think. I just don't understand, like, make this most recently used. That means I have to make the right pointer point to this one or something like that.
Our list is take this node self.cache of key and remove it from our list. And after we were...
Wait, why do I remove it? Oh. I get it now. It's this right here, right? And then self.insert. Oh, this makes sense. Right?
Remove it, then we want to reinsert it at the rightmost position. So we can just do self.
And let me try to insert this remove. So, or insert. I think insert might be easier because you're inserting it to the right. So it's self dot okay, so we got a temp variable equals self dot right dot previous. And now we got a node. And we got self dot right dot previous is going to equal to node, and node dot next is equal to self dot right, and then we're going to do node dot previous is equal to temp, and temp still has some. And then temp dot next is equal to node. I think that sticks right there. But I don't really get how to insert.
Get isn't so bad as long as we fill out these two helper functions for us. So now when we actually look at our put function, let's remember that if we have a key that's already in our cache, that means that a node already exists in our list with that same key value. So before we can insert this new key value pair, we want to remove from our list. So we can get that node by getting our cache and using the key value. So these remove from our list. So we can get that node by getting our cache and using the key value. So these helper functions are definitely coming in handy for us. So now we can create a new node with this key value pair. So node key value, and we can put that in our hash map. So now our hash map has a pointer to this node, but remember that's not enough. We also have a doubly linked list, so we need to take this node and insert it into our list. So insert and just pass in the node, which is cache of the key value. So the node is stored here and we pass that node into our insert function. Okay, so we just inserted a new value, but remember we have a capacity to worry about. So every time we insert a value, we gotta check, does the length of our cache now exceed the capacity? If it does, this is the part where we're gonna remove and delete or evict the least recently used. So we're going to remove it from the list, the linked list, and delete the LRU from the cache or the hash map. So how do we actually find the node for the LRU? Well, this is why we have our left and right pointers. Remember, the left pointer is all the way at the left, and it's going to tell us what the least recently used was. So left.next is always going to be the least recently used.
That makes sense.
And so first, we're going to remove it from our linked list by just passing in the node. And we're also going to delete it from our hash map. So self.cache. And we want the key of this node, which is actually stored in the node itself. This is why we didn't only store the value, we also store the key in our node class. So we don't have to return anything in put, but we do now have to fill out these two helper functions, remove and insert.
All right, so if it's in there, so if the key is in the cache, then we need to, I think this is done. Self.remove key. Wait, no, cache. Self.cache at spot key, right? Right, okay. And then now we need to put it in there somehow. So is it self.cache at spot key equals node key value? Is that how we did it? So we put it in there now, and right. Now we just gotta insert it, right? That makes sense. Self.insert self.cache at spot key, right? How do you check the length? If len, yeah. If len of self.cache is greater than self.capacity, I call it capacity, right? Then we need to remove the least recently used. So that's going to be, so least recently used self.left.next. Then we're going to delete that one. If self.left equals we just call remove on this. We just call it remove self.remove LRU, and then we delete it self.cache at spot key. I think that's what he has. Yeah, and how do you do
You
these?
now have to fill out these two helper functions, remove and insert. So if you have 3 nodes and you want to remove the middle node, what do? Well, you take this pointer and move it over here, and you take this pointer and move it over here. So this stuff is no longer relevant, and we have removed the middle node. This is going to be referred to as our previous node. This is referred to as our next.
Right, okay. That makes sense. So let's try this one. Let's do so getting prev of node. So it's going to be prev equals node.prev, and we're getting the next of the node, getting the next of node. And it's going to be next equals node dot, let's do nxt, node dot next. And now we're going to be switching we need to, what he just said, right? So we need to make this prev go to the next, and the next go to the prev. Skipping over where Yeah, I don't really know what I did wrong.
Next node. So when we're writing this function,
Is the insert one actually
is
harder?
going to be the middle node, so we want to get
It's not just self dot write dot prev. I don't know. What?
the previous and next nodes of node, so we can just get the pointer. So node.previous, node.next. All we want to do is say that previous.next should be updated and next.previous should be updated. These are the two pointers of the next and previous nodes. So previous.next should be next. Next.previous should be previous. So now node is no longer in between previous and next.
Yeah, okay, I did
The
that.
last thing we need to do is fill out our insert function, which what we want it to do is insert a node at the right
Man, I'm
most
surprised I
position.
can't figure this out. I feel like this should just be right. Self.write.prev equals node. Node.next, node.prev equals temp. Temp.next equals node. I don't know how that's wrong.
Right before our right pointer. So let's say this is our right pointer. We want to insert right here, and this is going to be our previous pointer. So when we have our new node that we're trying to insert, what we want to do is take this pointer and reassign it to this pointer, and reassign it over here. And we also want this node to be connected.
Right. Node.prev equals temp, node.
To its neighbors. So we're going to have the next
Dude, I don't
pointer
get how
over
my
here
code is
and
wrong.
the previous pointer to be
I did that.
here. So in this case, our previous and next pointers
1 sec.
we can get by using our rightmost pointer. So self.right.previous and self.right. Now we want both previous and next to point to node, so we can do that like this. Previous.next is going to be equal to next.previous, which is going to be equal to node. They're both pointing at node. Node has been inserted in the middle of them, and node.next and node.previous also need to be assigned to next and previous. So this is quite a lot of code, about 44 lines with some.
Yo, how is that different than what I wrote, y'all? How is that different than what I wrote? Okay. Why is it node.next? Oh, because I did it in reverse.
Some space and comments.
Hmm. No, my code is equivalent there.
In between, but this is how you get the most optimal solution for this problem. And of course I had a bug, so I misspelled something. I'm really hoping that's the only bug here because I do not want to search for a bug in these lines of code.
I don't either. Okay.
Okay, so we got it to pass. So I hope this was helpful.
What's wrong with my solution, dude?
Hey everyone.
Oh. Yeah, this problem's impossible. This problem's impossible, y'all. Yeah. Yeah. Man, this problem's tough. Hmm. Find the duplicate number. Didn't I do this one? How is this a linked list problem? What the fuck? Return true if you can partition the array into two subsets, where subset 1 equals subset 2. Let's just do this one, and then we can move on to the project. Okay. One 5 11 5. I don't even know like how I would do this, but I have this right here. How would I start? Would I go from like 1 5? Like how would I? Oh, equals sum subsets. Okay. Can I just have the sum of the array and then I try every combo? Yeah, I think that's gonna be bad because of this right here. All right, hold on. Can we partition? Hold on, I got a text. Oops. Drop my phone. Okay. Okay. Return true if you can partition the array into two subsets that. Yep. Okay. How would I do that with dynamic programming? I have no idea. I have no idea how to do this problem. What I can do is I can take the sum and then go through every single combo. So it's like the sum minus 11. Do those equal each other? Or the sum minus 1, the sum minus 6, the sum minus 17. And then do it again, and then do it again. I think that's how I can do it, but that's probably not what what's like the repeated work there? Like, is there like a choose, like what's the decision tree looking like? Like I can choose 1, 5, 11, or 5 again. And then after I choose 1, I can choose 5, 11, or 5. And this would be 1, 11, or 5. This would be 1, 5, or 5. That would be 1, 11, 5. So we can see there's definitely repeated work here, but I'm not really sure how to go about this. Like, it's like you have a DP of this length, and each thing is a sum subtracted by, I don't know, subtracted by the number at that index or something like that. I don't know. One, 5, 11, 5. I bet it can, bro. But how? But how? But how? But how? But how? And then from 5, I can choose. Well, it's not 5 anymore. It's, what's the sum of this? 11, 21, 22. So it's like 22 here, right? And then it's like, it's 21 here. And then it's 16 here. And then it's, what is that, 17 here? It's 11 here. It's 17 here. I don't really know what that does for me, man. Like, I really just have no freaking clue, bruh. 22, 11, 17, like, I don't know. I don't understand where the dynamic programming is coming in. Like, what we're, okay, like, you choose a 5 here, and then you choose a 1 here, right? So, like, that's repeated work. That's the same as this. Okay, these paths are equivalent. Or this path right here. Right? But how do I... Like, what do I do with that information? I don't know. Like, I just know that's going to be in the video. But I don't really know what I'm supposed to do with that information. I got the sum, and then I divide 1, 5, 11. Oh no, I need to add them as I go as well. This 22, and then it's right here. So I have 22, and I do minus 11, and then I have 11 left. Which means this is a match right here, so it's true. Can I like... Dude, I have no clue. I have no clue what to do. Man. 1, 5, 11, 5. 1, 2, 3, 5. But like, how would I store them? Like, what exactly am I storing? That's the question I need to answer. Like, in other dynamic programming questions, you're all deleted up work. Dude, I have no... Okay, I'm watching the video, guys. I have no idea. Like, after 10 minutes, I have zero clue where to go.
Hey everyone. Hey everyone, welcome back, and let's write some more neat code today. So today let's solve partition equal subset sum. So this is a pretty interesting problem. So we're given a non-empty array of nums containing only positive integers. We want to know if the array can be partitioned into two different subsets such that the sum of each of the subsets is exactly equal. Notice how that's basically saying if we can take one subset of the array, which is going to equal half of the sum of the entire array, right? Because if we partition it into two equal halves, right? Let's say the total sum was 22.
Okay, I got that
If we partitioned it into equal halves, then each of the halves would be exactly 11, right? AKA, one of the partitions is going to be half that of the total sum. So for example, in this problem, the sum is exactly 22. So we want to know, can we get a partition or can we get a subset of this array? Basically, we can choose any of the values, and can we get a subset such that it sums up to 11? In this case, the answer is yes. It's true because we can take, the single 11, that sums up to 11, right? And obviously, if there's one way to get half of the sum of the total array, then the remaining elements are going to basically equal 11 as well, right? So you can see that 1 plus 5 plus another 5 is going to be equal to 11, right? Basically, these are the two partitions. So as with many problems, let's just try to figure out what the brute force solution would be. So basically, let's start at the first element, right? And for every single element that we visit, we have two choices, right? We can either include this in our sum or we can not include it in our sum. And we want to basically determine every single sum that we can make with any single subset from this given array. And we want to know, does that sum ever equal 11? Because 11 is our target, right? If we sum this up, divide it by 2, we get 11. So we want to know if that's possible. So let's brute force it, right? So the first choice, we can either choose a 1 or choose nothing, right? Basically skipping that. So either our sum will be 1 or our sum will be 0, because initially our sum is 0. So the next value is 5, right? So basically for each of these paths, we can choose 5 or not choose 5. If we do choose 5 here, we'll get a 6. If we don't, we'll stay at 1. Otherwise, on this path, if we choose the 5, we'll get a 5 because we started at 0. So if we skip the 5, we'll stay at 0. Next, we get an 11, so basically continuing that, right? So I don't know if I'm going to have enough room for this. Okay, no, 11 plus 6 is going to give us 17 on this path. Clearly, we went over, so we would probably not want to continue down this path. But over here, if we skip the 11, we'll get a 6 still. If we take 11 here, we're going to get 12. If we skip it, we'll get 1, and et cetera, we'll get 16 here. Skip, we'll get 5. If we take 11 here, we'll get 11, skip, get 0. But clearly, we found our target that we were looking for. We don't really have to continue anymore, right? So basically, we can skip this last element. We found our target. We're going to return true, and we're going to go back up. So as you can tell, since every level of our decision tree, we're having two choices, right? And what's the height of this decision tree going to be? Basically, for every single element, right, we're going to have a decision. So let's say the input size of the array is n. So basically, our time complexity is going to be 2 to the power of n if we do a brute force method. So let's go back to the first step, basically the first element that we were at, and let's see if there's any repeated work that we can cut down on. So initially our index or our I pointer is at the first element, right? So basically we're at the beginning of the array. We can go down the entire array. We can choose any elements from here, and we want to know, can we sum up to the target 11? Now, once we take our two paths, right, we're basically going to say I is now going to be shifted to the next element, 5, right? And we had two choices. We could have either chosen the 1 or we could have skipped the 1, but clearly now we have a new subproblem. We already have a 1, so from the perspective of this decision, we're not looking for a target of 11 anymore, right? We're looking for a target of 10. We're looking for a target of 10, and not only that, but initially our I pointer was here, meaning we could have done the entire array, but now our I pointer is over
10.
here, so we're not even looking at the entire array anymore. We're looking at a subarray, basically the remaining elements of the array minus this first one. So if we were to cache this, our new subproblem would be target of 10 that we're trying to solve, and I is not at 0 anymore. Index is at 1. Similarly over here, we can see since we're at 0, the target is still 11, right? We are trying to sum up all the way to 11, but the index that we're starting at in this case as well is 1 now, right? Because we basically said we were skipping this element down this path, right? So now we want to know, is there a way that we can sum up to 11 basically just from this subarray, right? And every time we made a decision, we would continue to update these values, target and I, right? So as you can see, what are the dimensions of our cache going to be? If these are the two variables of our cache, what are the dimensions going to be? Well, clearly I could be any value in the input array. So the dimensions of our cache are going to be n, where basically n is the size of the input array, right? Because I could be at any value from 0 to n minus 1. And what about the target? Well, the target is basically the sum of the entire array divided by 2, right? So basically sum of nums divided by 2, or the constants usually don't matter in time complexity, so basically this is going to be the big O time complexity. Now this is technically better than 2 to the power of n because they do give us a pretty good limitation. Like the values in this input array are usually going to be, I think, less than or equal to 200. Now if they were really big, like if this could have been 1,000,000, clearly that would not be very efficient because our sum could have potentially been super large. search, but this is basically the best way that we can optimize it. So basically, if we did a
What?
get first search solution with a cache, like a backtracking solution with a cache, this would be the time complexity, and this would also be the memory complexity, because this would be the dimensions of our cache. But it's actually possible to improve the memory complexity a little bit with dynamic programming, and the time complexity is mainly going to stay the same as this, but the overall memory complexity can be improved. And let me show you why that's the case.
I'm so confused,
So
dude. I'm just always
we were
confused.
starting at this first value, right? And let's say we already knew all the possible sums that any given subset from the remainder of this array. Like basically what we could do is say for every single one of those sums, we would add 1 to it, right? So for every t, let's just call it t for now, in that subarray, we're going to basically be checking 2 things, right? Either if t is equal to target, right? Like some possible sum from this subarray totaled up to the target, then we would return true, right? Every possible sum that we could create from any subset in this subarray, and if it basically that's what t would be, and if that t happened to be equal to the target 11, then we would return true, right? Or if we took every single sum we could create from this subarray and added 1 to it, basically 1 because that's the only value left over here, right? 1 plus t equal to target. If that was also equal to 11, then we would return true as well, right? So basically, this is the recurrence relation that I'm trying to show you. And so this is basically the idea we're going to use for the bottom-up solution. So instead of starting here, we're going to work our way backwards. So we're going to start here. So, and this is very simple, right? So how many possible sums could we create from this subarray? Well, there's only one value here, right? We either take it or we don't. So the amount of sums we can create is going to be 0 or 5. And what I'm going to do is I'm going to be storing these values in a set. So let's say this is our set. So far we have 0 and 5. Next, what I'm going to do is I'm going to go to 11, right? We're going to work our way backwards. I'm going to start at 11 and I'm going to iterate through every single one of these. And I'm basically going to add 11 to them, right? So for 0, let's add 11 to it. That's going to be 11. I'm going to add that to our set. Let's look at 5. That's going to be 11. I'm going to add that. 11 plus 5 is 16. I'm going to add that to our set, right? Clearly, we can see we already found the target value, so we could return, but let's just keep going to see.
Nah, I don't really get it. This is -2 then. It's -2. Okay. Can I do this? I don't think I can do this. Wait. During iteration. Yeah, you can't do that. Wait, that is a useless case. One, two, 3, 4, 5, 6. I mean, I get it, I guess, but I don't understand how this is not brute force.
See all the possible targets we could create with this input array. So we were done visiting 11. Now let's go to 5, right? So basically we're going to iterate through every single one of these, add 5 to them, and then see if that's a new value. If it's already a value that exists, then we wouldn't do anything. Like in this case, we can see 5 plus 0 is just going to be 5, right? So I'm not going to add a second 5 to this because we already have a 5. This is a set. It's going to want only unique values. So we're not going to end up adding a second 5. But if we add 5 plus 5, that's going to be a 10. If we add 5 plus 11, that's going to be a 16. We already have a 16. If we add 5 plus 16, that's going to be 21. And basically, I'm going to do the exact same thing with 1. So, you know, we would add a 1 here. We'd add a 6. 5 plus 1 is 6. 1 plus 11 is 12. 1 plus 16 is 17. And 1 plus 10 is 11. We already have 11. 1 plus 21 is 22. So basically,
but you're doing repeated work, though. I don't understand. Like, why is this optimal?
List of sums we could possibly create from our given input array. As long as this set contains 11, we return true. If it doesn't contain 11, that means it's impossible to sum up to this target, so we would return false. Now, I think in practice, the size of this set is probably going to be about the same size as the cache that we would use in the memoization technique, but technically the size of this cache is going to be limited to the size of the target, which is basically limited by the sum of the nums input array. So this is going to be the memory complexity in this case. Technically, the time complexity is going to be the same. But I think this solution is definitely easier to code. It's just a little bit tricky to actually arrive to this solution. I think going through the brute force to the caching to the dynamic programming solution is the best thought process to arrive to this optimal solution. So now let's jump into the code. So one thing I didn't mention is that if the sum of our input array is odd, then it's obviously going to be impossible to partition it into an equal half, right? So basically, if the sum of this modded by 2 is 1, then we're going to return false. Also, I'm going to have a DP set, as I mentioned, because this is going to be the most optimal solution. To the DP set, I'm just going to add a base case of 0. Basically, we're guaranteed that we can add up to a sum of 0, right, if we just don't choose any elements from the input array nums. And the target that we're trying to sum up to is, of course, the sum of nums divided by 2. So with that being said, let's iterate through every single value in nums in reverse order. You could do it in regular order, but I'm just going to do reverse order because I'm used to it. So we're going to go through every target or every total value that's already in our DP set for every T in DP. And what we want to do is to DP add a value, right? We basically want to add T plus nums of I, right? Because I is
Yeah, but
the
you
current
can't do
index
that,
that we're
right?
at. We want to add, for every single t that's already in DP, we want to add nums of I to it, right? But we can't update this DP set while we're iterating through it. So what I'm going to do is create a new DP set, basically next DP. It's going to be the DP set that we iterate through over the next time we execute the loop. So instead of adding to DP, what I'm going to do is add to next DP. But we also don't want to lose all the original values that are in DP. So what I'm also going to do is to next DP, I'm going to add the T value as well, whatever the T value happened to be. Now, if I really wanted to, I could probably skip this line if I just took DP and cloned it and then set that to next DP, but whatever you prefer. Basically what I'm doing is I'm setting next DP, I'm taking every value in DP, adding it to next DP, and also adding this T plus nums of I to next DP. And once this loop is done executing, we're basically going to update, reassign DP to the next DP set. And this is going to keep executing. It's going to keep executing. I is going to start at the end. It's going to go all the way to 0. So then we're going to have gone through every single one. And at the end, we can return true if and only if the target happens to exist in DP. Else, we have to return false. And yeah, so this is the entire code, and it runs fairly efficiently. So this is about 50%. Now, I think it would probably be a little bit faster if, the first time we find the target value, if we just returned it. Actually, let me just, you can probably stop watching at this point. That was the entire solution, but let me just see if this actually does speed it up. So let's say if I happens to be equal to the target, we can immediately return true. Let me see if that does speed it up. Okay, so that actually did. So it's about twice as fast.
That was not. Oh, this is not gonna go up higher, I don't think. But yep, I mean it's slower somehow. That makes sense. All right, taking a break, I guess. I don't know what the. All right, just an all over the place day overall today, man. Okay. All right. Got some drum and bass playing. We gotta fix what we're gonna work on right now. We got a little music player project, pretty self-explanatory. The problem here is that when we create a new playlist with this add button, enter playlist name, test. It doesn't set the name right here, which is not cool. Not cool. Now, how do I fix that? I have no idea, to be honest. Dude, the thing is, I need to make this like... No, because it works. It's just a bug. Like, I think this is a JavaFX bug. Because, like, look. Like, it's the right name, right? If I, like, switch off and then switch, it works. See? That's the problem. What if I make the same name? Oh, like, that's fine. What if do I even need to fix this? Like test. Oh, but this doesn't update? So where am I? In here, right? It's in... Jesus, dude. It's in the search one. I need to get the layout. It's not right. Wait, so why can't I do this? That's why. Okay. So wait, why can't I access it in here then? What? Oh, because it's music player. There you go. Okay. Man. So how do I refresh it then? Where is this button even being used? Like, I don't get why I can't just do that. Man, what's going on with this app, dude? Like if I add this to second playlist, like if I'm here, right, and I add this to second playlist, this does not update. There's no way. The only way to update is if I do something. It's not what I want, though. Is it getting this layout? Like, what is it? Dude, I'm so confused, bro. I'm just confused. I'm just confused. I have to get this V-Box. Maybe that's the problem. Handle change, get layout. That's fun. Well, let's go to song search. Can I just do like playlist dot get layout or get VBox right here? Is it not a real playlist? Button playlist. Oh my fucking god. Wait, playlist is a button? Wait. What? Why is this test, bro? Whatever, we're keeping it test. No, we're not keeping it test. What is this even doing? Playlist selection. So is it playlist catalog dot get is that it? I don't think that's right. No, it is. Okay, what is this? It's not adding it. It's not refreshing. Where's the catalog? What is this? Public static final. Huh. Yeah, I'll do it. So I can't do... Like that's not allowed because of what reason exactly? Dude, the problem is I just have no idea what these errors mean. Like I just don't know what happened. Wait. Okay, when I choose this, I need to figure out, okay, success. Okay, click. Okay, so it's probably right here. Right? Right, guys? Why? Why? And it's an infinite loop again, bro. And I just have no idea why. Bro, how to use the debugger in this stupid language, bro? I'm on the wrong thing, bro. Oh, comments. Okay. Where's the fucking button? Debug, bro. How do I? Oh. How do I like? What? Dude, why can't I just update the layout of the thing? I don't understand it. I'm not even in the same, like... It doesn't even make sense. Why would it do that? What the... Bro. Dude, I really gotta learn how to use this debugger. This is like a real problem. Because I'm stuck. That's the problem. Get layout. There's an infinite loop happening somewhere, and I have no idea where it is. What is calling that? It's only on the combo box set on action. That's not what I'm doing. Dude, where is the infinite loop? I don't get it. So it's like if I take this, right, for example, and I just do this, that was a handle change event. Right? Right. Right. So then why can't I just... Wait. Wait, what is this updated thing coming from? Wait, what? Why is that updating it when I go previous? Where's the previous thing? Oh, it's in playlist. Right. So wait, why does previous make it do that? Get VBox. Play next. I don't get it. Like at all. So it seems that this updated is when I need to do. You guys can't see it. I'm realizing that right now. But I'm playing around with the thing, and this updated is what I need to call to update my layout. I believe. I don't know. I don't know. But the thing is, what's weird is it's here though. Like I don't understand. Like. Because I need to go song search here. I need to do. So what's the playlist? It's just song. Song dot get layout. Shoot. Can I get the buttons? Playlist. Daja. Where are the buttons? Oh, I can't. Hold on, why can't I do this? Why is that a cardinal sin? Wait, what? Wait, it worked. I swore I tried that before. I'm not even joking. Wait, it just worked though. With no problems. Wait, what? Okay, that's one problem done. Now we gotta go into here, I believe. And here. Yeah, we need. Playlist, new playlist. Is the problem is that it's not in there? If I do new playlist, get VBox, that doesn't work, right? My mom and I are talking about who we're gonna vote for. Drop a comment who you're gonna vote for. I'm just joking, guys. Okay, so if I do test, right? Is this gonna crash my shit? No, because the problem is once I create the new playlist, I want to set this to be the new playlist. Bro, okay. I don't even know, like. Okay, and then if we know it's not empty because we just freaking added one. Uncheck call to set value. Bro, I know what I'm doing, pal. We should probably update it too, so it's like something like that. I don't know. Let's try that. But the name is missing, dog. The name is missing. Param? What is that? Yep. Just very strong. That's me. What the fuck? What? Dude, it wants me to do so much stuff. I'm gonna just try this. I'm gonna just copy it, just see what it does, honestly. Yeah, bro, that really worked, bro. That really did something amazing. What the hell is a list cell, bro? What box set? Wait, what? Yo, this needs to run. This right here must run. But how? Because then I get an instant crash. Bro, I just want to get this feature done and then I'm done, bro. This is like actually just ruining all my happiness. This get layout needs to be called when I... Is it like, okay, which line is causing it to do that? This actually just might just not work. Yeah. Okay, so it's this line. Set playlist is the problem, right? What happens in set playlists? So why don't I just create a flag? Okay, private Boolean button change equals false. Band-aid to let me update layout after I add a playlist. Okay, hopefully okay, if button change, if not button change, right? Then we can do that. Button change equals false. Okay? And then we're going to do here button change equals true. But that's still going to not work the way I want it to. See? Bro. Okay. Oh, this should run set playlists. But it can't. Yeah, it infinite looped. Oh my god. Okay. I'm asking, bro. Okay. Sure. Good one, bro. That really worked, bro. Yeah, that really worked. It's fucking stupid. Wait, what? Dude. I don't understand why that's broken. Please, God, just let me fix this stupid problem. Wait, what? What? Nope. It worked. Oh my god, it freaking worked. Oh my god, it freaking worked, dude. Yes, it freaking worked. We need that to update. That's really weird. That seems to be working. Nice. Test. Please work. Yes. Oh my god, yes. Oh my god. I can breathe a sigh of relief. Okay, guys, I'm done. I'm done for the day. I'm done. I don't want to do anymore. Git add dot git commit dash m fixed add to playlist and creating playlist. Both work perfectly now and give immediate feedback. Oh my god. Just give me that. Just push it. I'm done. It's the best. It's the best thing ever. All right. Goodbye, everyone. Peace.